Here we introduce HeteroRefactor, a framework that ports programs into accelerators in one click instead of weeks. I'm Jason Lau from UCLA, advised by Professor Jason Kong.
Hello, I'm Qian Zhang from UCLA, advised by Professor Miyang Kim.
Large-scale software systems require high performance and energy efficiency. To achieve these targets, heterogeneous computing are used to port computation-intensive parts into accelerators. FPGA is a device whose circuit can be reconfigured as an accelerator. It often exceeds the performance of CPUs by several orders of magnitude, and at the same time uses less energy. But why isn't everyone using FPGAs if they are just awesome? The answer is they are extremely hard to program. The use of FPGAs is limited to their hardware aspects and requires weeks to months to program. 10 years ago, people have to write programs in hardware description language to use FPGAs. This language is pretty much assembly. There are no types but bits and instructions. There are no control flows but go-to statements everywhere. They made writing FPGA programs a nightmare. The good news is recent advances in high-level synthesis compilers liberate the developers. With high-level synthesis, you can now write an accelerator using a programming language that is similar to C++ without worrying about the low-level details, and that will be synthesized into hardware. However, we still observe significant gaps for software programmers. For example, even the largest FPGA nowadays only has tens of megabytes of memory. Therefore, developers need to optimize the bit width to save space, which depends on the input. Traditionally, they allocate integers with a fixed size bit width large enough for all possible input values, which wastes memory. Likewise, they need to tune the precision of floating point numbers to trade off between precision loss and memory. Besides, the FPGA tools do not support recursive data structures. Therefore, if you ever attempted to port a real software code to run on FPGAs, you will be frustrated to see a lot of errors. For example, in a simple binary tree, there will be 4 compilation errors. Nested pointers are not supported. Dynamic memory management is not available either, so users should pre-allocate fixed-size spaces by over-approximating the input. The types of allowed pointers operations are restricted, and all your recursion functions will not compile. After 30 years of evolution, we are surprised to see that even a C program written in 1989 cannot directly run on an FPGA. The developers have to manually rewrite the programs, which is a lot of hassle and can cause errors. They also have to over-approximate the bit width of integers, the precision of floating point numbers, and the sizes of dynamic data structures. This causes waste in the scarce on-chip memory. It's time for the software engineering community to lower the barrier for FPGA development. We had a dream. We had a dream that one day every programmer can just compile a software code for FPGAs. We had a dream that no one should worry about wasting the memory. We had a dream where there are no gaps between software developers and FPGA acceleration. We want to realize the dream where there is a tool to understand the code and refactor it.
Thank you, Jason. We proposed a new dynamic invariant analysis and automated refactoring technique called HeteroRefactor. It instruments the program to monitor FPGA-specific dynamic invariants, for example, the size of recursive data structures. Using this kind of knowledge, it automatically transforms the program to the runnable version with optimized bit width, and it selectively offloads the computation from CPU to FPGA only if an input falls within the dynamic invariant. Okay, here we go. Our first task is to make the original unsynthesizable recursive data structures synthesizable on FPGA. In the instrumentation step, we get the data structure size and the recursion depth using a set of typical data. Based on the collected invariants, we use the rules compiler framework to perform code refactoring based on these 3 refactoring rules. This is an example recursive binary tree program. To rewrite the dynamic memory management, we pre-allocate an array with the monitor size. We replace the malloc and the free with our implemented node malloc and node free, which returns the index of an array, and we replace the tab of return pointers to the offset of elements in the array. These tab changes are propagated to the entire program. Then we change the pointer accesses to array accesses using the offset value. Finally, we transform recursions into iterations based on the stack. Okay, in addition to make it run on FPGA, resource efficiency is another important concern. Traditional FPGA design requires a programmer to define the bit width for their variables. HeteroRefactor automatically finds the minimum bit width for integers and floating points. For integers, we first monitor the FPGA-specific dynamic invariants, like their value range, by Kvasir-based instrumentation. Based on the observed data range, we modify the integer tab with custom bit width to represent its max value. For the floating point tuning, we design a probabilistic differential execution-based approach. It first generates program variants with different precisions by source-to-source transformation. For example, we use Rose compiler to get two transformed versions, one with reduced precision and another one with original precision. After getting these variants, we measure the precision loss using differential execution. We add a verification function to check whether the error is within the threshold or not. We call this one sample of verification. So apparently, one sample is not sufficiently reliable. Therefore, we use Hofstad's inequality to calculate the minimum number of required samples to achieve our confidence level probability. With reduced bit width and data structure sizes, we may have input that validates the invariant at runtime. To ensure correctness, we add an input check on the host and an immediate check on device. Whenever the error happens, the host will restart the computation on CPU. Okay, from our evaluation, HeteroRefactor automatically transforms the original unsynthesizable code to the synthesizable version with no human effort required. And automated refactoring can reduce the human effort by 49% if we compare the manual code with the original code. In addition to make it run automatically, we also demonstrate the efficiency of our resource optimization. For different types of kernels, we achieve significant resource reduction of about 50% and increase the maximum frequency for some cases. Thank you for all support of this work. To sum up, we adapt the automated refactoring to heterogeneous computing with FPGA, and this combined dynamic invariant analysis and the automated refactoring technique is unique to the best of our knowledge. Thank you.